Alright guys, so last time we were looking at projectile motion, we looked at problems where we had a horizontally launched projectile. So we went up to some height, like on top of a cliff or on top of a building, and we shot our projectile straight to the side. Today we're going to focus on problems where projectiles are actually shot at an angle with relation to the horizontal. So there's really two ways that could be done. We could have our projectile launched upwards at an angle, so we have V0 and some angle theta above the horizontal, or it is possible if we're up on top of a cliff or a building or something to launch our projectile at a downward angle, so we have V0 and we have some angle theta below the horizontal. Now when we have projectiles launched at an angle, we always want to break that initial velocity up into a horizontal component and also into a vertical component. Now you'll notice that I've called the horizontal component just Vx, but I've called the vertical component V0y. And the reason for that is, remember that for projectile motion problems, Vx is a constant, but Vy can change. So the V0 can be split into Vx and V0y. Now, as you can see here, we've created right triangles, and so we can use trigonometry to solve for V0y and Vx. Since the sine of theta should equal the opposite, which is V0y, over the hypotenuse, which is V0, we can always say then that V0y will equal V0 sine theta. And for the picture on bottom there, that would have to be a negative value. For this picture on top, that would be a positive value, but they both be equal to V0 sine theta. And for our Vx, since it's adjacent, we can say that cosine theta will equal Vx over V0. So Vx will always equal V0 cosine theta. So now we're ready to talk about problem type 2. And problem type 2 is when we launch the projectile at an angle, but delta y for the whole process equals 0. Another way to name that is kind of a ground-to-ground problem. So if we see in the picture here, we have a ball or a projectile on the ground, and we shoot it up at some angle, or if it's a ball, maybe we kick it at some angle. And what it's going to do is follow a parabolic path and then come back down to the ground. Okay, and since at the end it's back on the ground, just like it was at the beginning, the delta y for the whole process is 0. Another point that we're usually going to care about for this type of problem is this highest point right here, and this highest point is referred to as the apex. So for any projectile motion problem, we're going to split our stuff up into horizontal components and vertical components. And so there's a few things we need to know. So for the horizontal, of course, we know that Vx equals V0 cosine theta. And we just talked about y just a minute ago. And for the vertical components, we know that V0y will equal V0 times the sine of theta. Of course, in the vertical direction, we also know that A equals -10 or -9.8 meters per second squared. And since this is a ground-to-ground problem, we know delta y at the very end is going to equal 0. Another important thing we need to realize whenever we're asked to solve anything for the apex is that the velocity in the y direction at the apex will always equal 0. Because as the projectile is moving up, it has an upward vertical velocity, and then when it's coming back down in the second half, it has a negative or a downward vertical velocity. And so during switching from a positive velocity to a negative velocity, that vertical component of the velocity has to equal 0 right at the apex. Alright, so for this example problem, we have a ball that's launched at 5 meters per second, 45 degrees above the horizontal, and it's launched from the ground. And then it lands back on the ground, and we want to know how long is it in the air, how far does it go while it's in the air, and what is the maximum height that it reaches, or the height at the apex. So for our horizontal information, we know that Vx is going to equal 5 times the cosine of 45, which is equal to 3.5 meters per second. And then for our vertical information, we know that V naught y equals 5 times the sine of 45, which is also 3.5 meters per second. Since we have a 45-degree angle, those two components are equal to each other. We know delta y at the end equals 0. We know A equals negative 10 meters per second squared. And we know V at the apex is equal to 0, the vertical component. The velocity at the apex equals 0. Alright, so if we want to figure out how long it's in the air, we can say delta y at the end equals V naught yt plus 1/2 at squared, and delta y at the end equals 0. So negative V naught yt equals 1/2 at squared. This t cancels out with one of those t's, and we get that t equals negative 2 V naught y over a. So we get negative 2 times 3.5 divided by negative 10. So 7 over 10, and we get a time of 0.7 seconds. Next, we're going to figure out how far it goes. So what we're doing is looking for delta x at the end, which will always equal Vx times the total time that it's in the air. So Vx, we already said, was 3.5 meters per second. And the time that we just solved for was 0.7 seconds in the air. So we take 3.5 and multiply it by 0.7. And that comes out to about 2.5 meters. Finally, we're looking for the maximum height reached by our projectile, or the height at the apex. So for that, we don't really know how much time it takes to get to the apex, although it is half the total time for this problem. But let's just assume we don't know the time to get to the apex. But we can do V at the apex squared equals V naught y squared plus 2a delta y. And V at the apex we know is equal to 0. Rearrange for delta y, we get that delta y at the apex is equal to negative V naught y squared divided by 2a. So we get then negative 3.5 squared divided by 2 times negative 10, and we get about 0.61 meters. So we found that our projectile was in the air for 0.7 seconds. It traveled 2.5 meters in the horizontal direction while it was in the air, and the highest point that it ever reached was 0.61 meters along the ground. So we're going to do one more screencast on projectile motion looking at problem type 3, and that's when we launch at an angle but delta y at the end is not 0.